Hope you guys are having a good start to your day. A little bit of a downer that the Bobcats lost last night, but we don't have to talk about that anymore. It was a good game. They nearly won. And if they had played one more quarter, I think they would have won. At any rate, so today is Friday. How about Friday? It's Friday the 13th. And we are going to kind of continue where we've been talking or what we've been talking about. So just as like a super quick review, if you remember on Monday, what we talked about was, excuse me, on Monday, we discussed basically subatomic particles. We talked about, what a molecule is made up of. And we talked about, the different properties that the different components that an element or an atom has. So subatomic particles. Then particles. Then on Wednesday, we talked about scientific laws. So conservation of mass. And then on Friday, we discussed, electrons, those subatomic particles, and how they determine the chemical properties of an atom. So atoms can do different things. For example, an atom of, let's go with helium, versus an atom of sodium. Helium is classified as one type of element. It's referred to as a noble gas. And then sodium is a metal. They're classified differently, in part because they behave differently. Sodium, if you drop it in water, it's going to basically ignite. It's going to very violently react with that water. Whereas helium, if you were to get like a small amount of helium and put that in water, it's not going to have the same effect. Helium gas, for instance, you've inhaled helium gas and listen to a voice like this. Those are all related to the properties of these different elements in different atoms. Now, what ultimately has a huge impact on the functionality of an atom and basically how something behaves is the electrons. So this is kind of a classical experiment. This is piece of instrumentation right here is a spectral tube holder and a power supply. And what this allows you to do is to get a gas. For instance, here we got hydrogen gas, H2 gas. And then you send an electric current through it. And then you can see the different colors that are produced, provided that you use a prism. So can I get a thumbs up if anyone's ever heard of the band Pink Floyd? Okay, we got one thumbs up. Great. Of course. Okay, fantastic. So Pink Floyd has an album called Dark Side of the Moon. And on the cover of that album, there is a piece of glass known as a prism. And that piece of glass, you send white light through it, and then you get all the different colors of the rainbow and everything in between. Your primary and secondary colors, all the colors of the rainbow are produced. And what that's showing is basically the white light that's sent into the prism. It's actually not just a single color. Instead, it's several different colors. Now, that's all relevant because lights of different colors have different amounts of energy or different energy associated with them. Now, with this instrument right here, this hydrogen discharge tube, you can produce a singular color whenever, this tube has a gas like hydrogen in it. And what's helpful is, or what's pretty cool about that is here, whenever we send, like if you send an electric current through hydrogen gas, it's going to give kind of this magenta color. And you're going to see it and you're going to be like, ooh, magenta, fantastic. But then if you hold a prism up to that, what's going to happen is that prism is going to show the different colors that are kind of concealed, or the different colors that make up that magenta. And in the case of hydrogen, you've got blue, kind of a light blue, and then a pretty brilliant and bright red there. So hydrogen gas produces these three different colors when you're looking at the pigment that's produced from that gas under a prism or through a prism. This is what's known as a line spectrum. So above here is the hydrogen line spectrum. Now, can I get a thumbs up if you think that different gases will produce different line spectrum, and a thumbs down if you think, oh no, they're going to all produce the exact same one? Okay, got some thumbs ups. Okay, now I did use my tone of voice to definitely discourage that, oh no, different, the exact same. Every single substance is going to produce different colors. And some examples of these. This is that pigment that you get from hydrogen. If you were to use the element neon, Ne, you're going to get this kind of brilliant, it almost looks like a lava color. Nitrogen will produce this, helium will produce this. Now, if you were to expose all of these to a prism, well, then you'd be able to dissect and see all of the different colors that are kind of concealed and behind that. Another way to visualize this, and what this is all getting at, is every element and every atom of every element has different electrons in different places. Now, on Monday, we talked about how many electrons a given element has. Here we've got what's called a flame test. And what this is basically taking a small amount of different substances: boron, sodium, lithium, potassium, iron, barium, strontium, calcium, and copper. These are all metals, and exposing them to a flame. What color is produced whenever you burn them? If you look at the one that I always like to highlight is barium. Well, if you look closely at barium, it's almost like you get a little bit of that exposure as to if you were to look at it through a prism, because if you look closely at this barium flame, thumbs up if it is one color, thumbs down if it's more than one color concealed there. Okay, we got thumbs down, yeah. I mean, if I look right here, I see a blue, and here it's green. So I was really aiming for you to see that there's multiple colors there. And that's because, oh, I like it, Aaron, with the triple thumbs down. All of these different, or there's different colors here that respond, or that are related to different wavelengths of light. Now, with that in mind, let's go ahead and try to deduce what this is. So I'm going to launch a poll here. Which metal might be in this party candle? So we've got, go ahead, I'm going to launch my poll. Look at this in a comparison to the others. And this sort of question is a good one that I could use on an exam. I wouldn't expect you to remember this or recall this. But this is like one that I could use on an exam. And I say I could because of the fact that, well, these are high resolution pictures and you're going to be taking your exam on your computer, so I don't have to worry about printing them and, degrading the quality of the picture. Let's see if we can get up to, let's go for 65% participating. We've got 59, so I need about 5 or 6 more people. I can give you another, okay, 5, 4, 3, 2, 1, 0, and pull. I delayed my 0 there because, um, because I was confirming that I'm recording, and I am indeed recording, so that's always good. Okay. I will make sure that, yeah, I will make sure that we're good there. I had somebody ask about, yeah, color and color blindness. So yes, I will make sure that I'm asking about ones that are not distracting there, or not a problem there. Okay, so what we've got here is, well, everyone voted for lithium. Almost everyone. And you're right. All that we're doing here is looking at the colors that are highlighted here and comparing them. So, okay. If we have our options, boron's got kind of a green and blue. I see a little bit of a blue and purple there, so you could make a case for a small amount of boron, but let's see if there's a better option. Okay, next up was barium. Well, barium's kind of similar to boron. The only difference is that barium's a little bit more kind of almost photo bleached. It's a little bit fainter, but still kind of the same color patterning. Copper, copper is similar to boron as well. Lithium, however, lithium's got a really strong, brilliant, bright red, and we see that bright red. In our candle here, it's a red and yellow combination there. So I was looking for lithium as the correct answer there. Now, with that in mind, we've got a model and a way to basically, sorry, I've got markings on my screen. They're not there though. Okay. What this all boils down to is this right here. This is what's known as a line spectra. And what this tells us is the energy related to our different compounds, our different solution, or our different atoms, different electrons in an atom, and the different energy levels. So if anyone's ever seen like the UV or ultramagnetic spectrum, you can relate a wavelength of light, for example, here, here, and here, to a particular color. So what this tells us, what's happening is that we have in hydrogen gas, for example, we have electrons that start at this lowest energy level. And then you kind of electrocute them in the sense that you send an electric current through them, and all those electrons that are basically minding their own business, well, they get shot up to different energy levels. And then as those electrons that are shot up to these higher energy levels kind of relax and settle back down, they produce a color. So it's this excitation, excitement of electrons, followed by relaxation, so in a sense, relaxation that produces different pigments. So an electron going to a high energy level and then settling back down is going to release a color. An electron going to a not quite as high level and settling back down is going to produce a different color. Now, the value of this and the importance of this is this basically gives a sense of where an electron is. It gives an idea of, okay, well, if an electron goes up to this high energy level and then settles back down to a lower level, well, then that's where it must be. That's where it is. That's where it likes to exist. So these different pigments give an idea for what we see here. When we think about the overall composition of the visual of an atom, In the center, we've got our nucleus, where we have our protons and neutrons. P, 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 N, N, N. Our protons and our neutrons are in the center, in the nucleus. Outside of there are your electrons. Okay. Now, imagine that this is kind of our ground state, our starting point. We've got our starting point where these electrons are, and then you send an electric current through it. This electron right here, it's going to shoot up, and then it's going to settle back down to here. And whenever it settles back down, that's going to release, or let me rephrase that. That's going to produce, let's just say that's going to produce our purple light. Okay. This electron right here, that is at a higher energy level because it's farther from the nucleus. This electron that's farther from the nucleus, that's going to get shot up, and then it's going to settle back down. And whenever that settles back down, that's going to produce green light, for example. So then if we've got an electron way out here, and that gets shot up to a high level, that settles back down. Do you think that's going to produce, go ahead and give me a thumbs up if you think that it's going to produce a different pigment or if it's going to produce purple or green. If you think it's going to produce something purple or green, give it a thumbs down. If you think it's going to produce a different color, give me a thumbs up. Okay, so this is going to produce something other than, let's call it red. So essentially, these are just kind of randomly thrown out colors. What essentially that means is this study of this was basically a way to say, oh, okay, well, we've got something that, there's an element that whenever we excite it, it produces two colors. So then if it produces two colors, then we have this kind of conclusion where, oh, well, that means it's got electrons only in two locations. Because they get shot up, they settle back down to two different places because there's two different colors. If you have a substance that produces electrons that give you 8 different colors, how many different places do you think those electrons could possibly be if something produces 8 colors? Do you think that it would be 2? Do you think it would be 1? If you're producing 8 different colors, how many different places do you think electrons could be? Go ahead and add to the chat. I'm going to write it 8. Perfect. 8. If you've got 8 different colors that are generated, then you probably have 8 different places that electrons are going to be found. So this is super helpful because then it's almost like, okay, well, we've got a nucleus. We know our protons and neutrons are in there. And then we can send energy through something, look at it in a prism, and we see 8 different colors that are produced. That tells us our electrons are probably in 8 different places. Does that make sense? Give me a thumbs up if that makes sense, or a thumbs down if I'm still confused. Okay, we got some thumbs up. Okay, cool. Now, if you're a little bit confused by this, just be patient with yourself. This is definitely it's very kind of weird. I would say that I would describe it as abstract. It's like, how do I wrap my mind around this? The entire intent and the purpose of this, I'm going to jog back a couple slides. The purpose of this right here is to basically figure out where electrons can possibly be. So that's what we're looking to study. Where can electrons possibly be? And we can figure that out based on the different colors that are produced. Now, with that said, here's where it gets really it gets a little bit sideways. Now, the way that I always like to think about this is I like to think about this as I am trying to basically visualize where I can put my different electrons. And actually, I'm going to jump ahead to the next slide because that's really helpful for me. And I think that it's overall helpful when explaining this. So let's imagine that we have, let's go with boron. Add to the chat, how many electrons does boron have? How many total electrons when it's neutral? One way that we can figure that out is 5. Perfect. It's got 5. We know that it has 5 because this number right here, that 5 indicates how many protons it has. And if it's neutral, then it has no charge. 5 protons have to be offset by 5 electrons. Okay, so we got 5 electrons. Now I'm going to jump back here and we're going to work through this and we're going to say, okay, where are borons, B's, 5 electrons? Where are borons 5 electrons? And I'm going to draw, so these little arrows here for Z, Y, and X, I'm going to draw that as well because we're thinking about this in 3 dimensions. I'm going to draw a dashed line to indicate my Z axis, the one that's coming out of the page or going into the page. Z, Y, X. Okay. There's my 3 different axes. So I got this in 3 dimensions. Now at the center, I'm going to change my color. I'm going to go with I'm going to go with black, and I'm going to color the origin black because what that indicates, or what that's showing my origin. That's showing my nucleus. My nucleus is where all my protons and neutrons are. I don't really care about anything else because what I'm interested in here is I am interested in where my electrons are. And so when we think about placing electrons, we think about them in increments of 2, or we start out thinking about them in increments of 2. Now, what this means is I've got a total of 5 electrons. 1, 2, well, let me erase that. I've got 5 electrons that I can place. Electrons are negatively charged. Where do you think my electrons are going to be with respect to my nucleus? They have opposite charges. So what do we know about a positive and negative charge? Do they attract or repel one another? Add to the chat your thoughts on that. If one thing has a positive charge, what's it going to do to a negative charge? If our nucleus has a positive charge, it's going to attract negative charges. So we want to, like the positive nucleus, I'll say positive nucleus attracts negatively charged, or I'll just say negative electrons. Okay, so for my electrons, I'm just going to use little green dots. So I'm thinking about these in increments of 2. So my first 2 electrons, they are going to be as close to my nucleus as possible. There's my first 2 electrons. Now we're thinking about this in 3 dimensions. So these 2 electrons, like if we use this baseball to depict a sphere, and imagine the center of this baseball is where my nucleus is. I've got one electron on this side of the baseball, and it's on the outside of that. My other electron can be as close to the nucleus in the center of this baseball as possible. And they kind of have this this pendulum type of effect where they'll go back and forth. And they're both of my electrons, my first two electrons are really trying to get to the center of my baseball. They're trying to get to the center of that X, Y, and Z axis. So what that means is if one of those electrons drives to the center of the nucleus, what's it going to do to the other electron? I saw somebody say repel earlier, and that's going to repel it. Even though both electrons are attracted to the nucleus, they're both kind of pushing one another. And so when one gets close, the other gets farther. So what that means is that these two electrons, these first two lowest electrons, they're most likely going to be in the center of that, or yeah, they're going to be occupying like a spherical space. So that's my first two electrons. And we use these subshells, and we say, okay, well, the first two electrons are in the 1s subshell. So if we're trying to come up with basically a map almost, a description, a like text description of where these electrons are, we use something called electron configuration. And we say 1s2. This tells us our subshell, S, and the number of electrons that those electrons are in, or the number of electrons that are in that subshell. So if we jump over here, we kind of refer to different parts of the periodic table with this sort of notation. So whenever I'm trying to get to boron, I'm going to say boron has an electron configuration that is 1s2. That's where the first two electrons are. Okay. After that, my next two electrons. So now I'm down to 3 electrons to place. Well, those next, so I'm still thinking about this in increments of 2. So I've got my 1s electrons, those are placed. Those are as close to the nucleus as possible. Then my next electrons are going to try to be as close to the nucleus as possible. But keep in mind that those electrons in the 1s orbital, well, they don't like the tendencies of the 2s electrons or of those 2s electrons, because they're like, wait. We want to be close to the nucleus. We don't want you to be close to the nucleus. So we're going to, those 1s electrons are both attracted to the nucleus, but then also repelling those 2s electrons. So the first two electrons are in this green sphere. The next two electrons are going to also be in a sphere. And I'm going to use blue to depict that. And that sphere is slightly larger. Electron, electron. Okay. Now, where it gets complicated. Okay, so before I proceed, I've got 2 electrons in the 1s orbital, then 2 electrons in the 2s orbital. How many electrons have I put down, and how many do I have left? Go ahead and add to the chat the number of electrons that I still have to place for boron. 1. Just 1. I have my last one to place. So I've got the first 2 electrons in every single element. The first 2 electrons in every single atom of every single element, those 2 electrons are in the 1s orbital. The next 2 are in the 2s orbital. The next 2 electrons, the next electron, our 5th electron, well, it's going to be in the next subshell. Our next subshell is known as the p subshell. So that p subshell we label that as our 2p subshell. And now what I want you to do is I want you to look at this right here. These three different models, p sub x, p sub z, p sub y. P sub x, p sub y, p sub z. Okay. Notice how this p orbital or this p subshell is sometimes referred to as being a dumbbell. And the reason that it's referred to as a dumbbell is because it kind of has that like bulbous shape. Kind of looks like a dumbbell, where here's the weight, here's one weight, and here's the other weight. Okay, so that's where we get the dumbbell term. Now, 2 electrons can fit here. 2 electrons can fit here. And 2 electrons can fit here. So add to the chat if each px, py, and pz can hold 2 electrons. Add to the chat how many electrons a p subshell can hold total. And I'm just talking about the p subshell. We got votes 1. So this one right here can hold 2. This one can hold 2. And this one can hold 2. 6. Now, I think the people who are answering 1 were thinking about boron, and you're right, we have 1 electron left. But when I mention a p subshell includes px, pz, and py, all 3 of these. So if each one of them can hold 2, that means a p subshell can hold 6, because it's 2 plus 2 plus 2. Now, with that in mind, I'm going to erase all this. Now, if we go back to thinking about boron, okay, so my first 4 electrons were held in 2 spheres, the 2s and the 1s subshells. My 5th electron, imagine that I've taken this right here and overlaid it right here. That means I've got about my x-axis, this kind of like dumbbell shape. I can have an electron like right here. Kind of looks like elephant ears, basically. One of my electrons can be there, in which case that gives me the opportunity to complete my electron configuration and say 2p1. I don't have to say 2px or 2py or 2pz. I just have to say what subshell it is, the p subshell, and the number that goes before that. So if I give you, this is what's known as an electron configuration. Anytime you see an electron configuration, you can use that electron configuration to figure out what element you're talking about by adding up these exponents. 2 plus 2 plus 1 is 5. So that is the electron configuration for boron. Now, if I give you, let's go over here. And let's imagine, and you can, this PowerPoint is posted as a PDF as well. If I gave you an electron configuration of 1s2, 2s2, 2p5, I'm going to ask a couple of different questions and add your response to the chat. How many total electrons does the element that I'm talking about, or an atom of the element that I'm talking about here, how many does it have? How many electrons does it have? Perfect. Great job. 9, because you just add the exponents. Okay, now my next question is, what element am I talking about? Add that to the chat. And you can just use the symbol or you can write the full name. Fluorine, perfect, wonderful, fantastic. That's all there is to that. You just have to add the exponents and then look at the periodic table. And you see, oh, well, 9 electrons. Okay, fluorine, when it's neutral, has 9 protons and 9 electrons. That's what I'm looking for. Okay, then if I were to go on and say, what element has this electron configuration? 1s2, oh, sorry, that should be 2s1. Go ahead and add to the chat the symbol for this element. Perfect. Lithium, Li. Fantastic. That's awesome. Great job. Okay. Now, the entire intent of all of this is to basically build on this right here. So this was when people did these excitation experiments and they said, okay, well, there's X many different colors. That's where the electrons are. We've got 6 different colors, so that means there's 6 different places where electrons can be. Then immediately it's like, okay, cool, that's great that we have 6 different places, but what are those 6 different places? People took that and said, okay, well, they came up with what are known as atomic orbitals. They came up with this is almost like the blueprint for a house. If every electron or electrons live in different rooms in a house, this is the blueprint for that house. These are where those electrons are. That's what really we're getting after here, where it's like, okay, cool. Well, I think the electrons are there, and this is what that room looks like that holds so many electrons. So does this look at all like a house? No, it doesn't. But this is taking place at what's known as the atomic level. We're talking about something extremely small, visualizing and theorizing where electrons are. Now, with that in mind, I'm going to clear all my drawings off of this page. These different subshells, there's 1, 2, 3, 4 different subshells. These different subshells correspond to different parts of the periodic table. For example, the S subshell corresponds to the S block. There's 2 rows in the S block, and the S block or S subshells can hold 2 electrons. So anytime you see an electron configuration, and I'm just going to put an X for a number, it will be XS1 or XS2, because the S subshell can hold no more than 2 electrons. The P block, I'm going to go ahead and put XP1, XP2, XP3, XP4, XP5, and XP6. Okay. That is because the P subshells can hold a maximum of 6 electrons. Okay, so think about that. The P subshell can hold a maximum of 6 electrons. Now let's jump back. The P subshell has a maximum of 6 electrons. 2 can go in here, 2 can go in here, 2 can go in here. The S subshell can hold a maximum of 2 electrons. 2 electrons can go in there. Now, with that in mind, can somebody make an approximation or an educated guess about how many electrons is the maximum number of electrons that the D subshell can hold? Alex was quick on, yeah, Alex and Savannah, you're absolutely right. It's 10 electrons. Because each of these configurations, that holds 2, that holds 2, 2, 2, 2. Now these sort of shapes, these spheres, or these kind of oval-shaped spheres are like mathematical models for where those electrons could potentially be. Okay, so Now, let's go on to the F subshell. Make an approximation as to how many electrons the F subshell can hold. I knew it. I knew, Alex, I knew you were going to hit 14 and get it right. You're absolutely right. Each one of these depictions, that holds 2. Maximum of 2, 2, 2, 2, 2, 2. These are fantastic questions. Maximum number of electrons that a subshell can hold. Okay. Now, with that in mind, that I think is helpful when it comes to doing an electron configuration, because you can use that information combined with the rows on the periodic table. 1, 2, 3, 4, 5, 6, 7. So I like to take an example like chlorine. Add to the chat, how many electrons does chlorine have total? Perfect. 17. Well done, everyone. Now, what I want to do is go ahead and work through, where do I put all those electrons? What I need to do is I need to recognize that chlorine is in the 3rd row. So the first place, the first 2 electrons that I'm going to place are in what's known as the 1s orbital. That's 1s. I got 2 in there. What I like to do whenever I'm doing something like this is I basically cross electrons or cross elements off. Helium has an electron configuration. If you look closely, helium's electron configuration is 1s2, because helium only has electrons in that 1s subshell. Helium doesn't have any electrons in the 2s subshell. I can cross that off. Okay. Now I'm going to go to 2s because I use this number, the number row, and then the next subshell. And I use the subshell corresponding to the block. So this is S block. So this is 2s2. Where do I go next? After 1s2, 2s2, where do I go? What's the next thing that I should write? I'm going to go with 2p. Layla, fantastic. 2p. And I've got a complete p block, or p subshell, or 2p subshell. So I'm writing 2p6. Great job, Layla. Then my 3 and my next S block is full. So 3s2. Then I'm going to jump all the way across the pond over here. And I'm going with 3p because I'm in the p block. 1, 2, 3, 4, and 5. So based on this notation, I can add up my exponents. 2 plus 2 plus 6, that's 10. Plus 2 is 12. Plus 5 is 17. That's what I get to. Now, what we're going to do is we're largely going to stay in that first 3, or those first 3 rows. Now, this is really complicated. This is really like, what on earth am I can't visualize this. What is most helpful for me is to do something like what we did over here, where we said, okay, here's my axis, X, Y, and Z planes. My first 2 electrons go in the 1s orbital. That's a sphere. My next 2 electrons go in the 2s orbital. That's also a sphere. My next electrons are able to go in the 2p orbitals. And there's a total of, the 2p, which there's 3 of those subshells. I can place 6 electrons there. So if I have an electron configuration of 1s2, 2s2, and 2p6, what element has the electron configuration of 1s2, 2s2, 2p6? Write the symbol for that, or type the symbol for that. jump over here. So, oh, I'm going to clear all my right ratings. Perfect. Charlene, great. Neon, you're absolutely right. And I see, it was, I think Ryan, you had it for great job. You're absolutely right. So that's our electron configuration. That's the thing, that's the skill that I want you to be able to do, to take an electron configuration like this and convert that to what's the symbol, and vice versa. Now, I'm going to go ahead and stop right here. We're going to pick this up again on Monday morning. I'm going to go ahead and stop my recording.